Hi, in this video, we are going to look at convex functions and Jensen's inequality. This is the last video in the section on advanced inequalities. So let's get started. We have let f of x be continuous on an interval I if for any two numbers, x1 and x2 in I, we have the following: f of x1 plus x2 by 2 is less than or equal to f of x1 plus f of x2 by 2 is always true, then we say that f of x is convex in I. That is another way of saying that it is concave up. So what is the meaning of this? The function should look like this. The graph of the function should look like this. So if you have x1 here and x2 here, we can show that the midpoint of this straight line segment joining x1 comma f of x1 and x2 comma f of x2, this point is x1 plus x2 by 2 and f of x1 plus x2 by 2. And you can see that this f of x1 plus x2 by 2 is higher than this point, which is basically, actually I have made a mistake here. The y coordinate of this would be f of x1 plus f of x2 whole divided by 2. That is the midpoint of these 2 points, right? And that is higher than this point, which is x1 plus x2 by 2, comma f of x1 plus x2 by 2. So we can say that this is bigger than this, and that is what it means to be a convex function over the interval, right? As long as this property is satisfied by any two x1 and x2 in that interval, we say that f of x is convex in that interval or concave up, right? And if the opposite is true, f of x1 plus x2 by 2 is greater than equal to f of x1 plus f of x2 by 2, then we say that f of x is concave in that interval, or we say that it is concave down. The shape of the function's graph will be like this. This is concave down and this is concave up, or convex function, and this is a concave function, right? Now, there is a simple theorem to check concavity or convexity. The theorem says that if f of x is twice differentiable in the open interval a to b, we have convex function f of x in a to b implies f double dash x is greater than 0 in a to b, and concave f of x implies f double dash x is less than 0 in a to b. So that is our definition of concavity and convexity. And now from there, we can supply Jensen's inequality. So what is this inequality saying? It says that suppose f of x is convex in I, then for any x1, x2 till xn in I, we can say that f of x1 plus x2 plus xn by n will always be less than equal to 1 by n f of x1 plus f of x2 till f of xn. So this is the Jensen's inequality. And the equality here is valid when x1 is equal to x2 till xn. When all the points are identical, then we have the equality. For concave functions, the inequality sign is reversed here, and this becomes like this for concave functions, right? Okay. One corollary of Jensen's inequality that you should be aware of is this one. Suppose f of x is convex in I, then for any x1, x2 till xn belonging to I, and any non-negative numbers lambda 1, lambda 2 till lambda n satisfying lambda 1 plus lambda 2 till lambda n equal to 1, we have f of lambda 1 x1 plus lambda 2 x2 plus lambda n xn is always less than equal to lambda 1 f of x1 plus lambda 2 f of x2 plus lambda n f of xn. And the equality is again valid when x1 and x2 are all equal. Now think about this. This statement is like saying lambda 1, lambda 2. If we choose lambda 1, lambda 2 till lambda n as 1 by n, we'll get the regular Jensen's inequality. Because this side you will get x1 plus x2 plus xn by n, and this side you will get 1 by n common, f of x1 plus f of x2, and so on till by n, right? So that becomes your regular Jensen's inequality. So this is like a generalization of Jensen's, right? The condition is lambda 1 to lambda n add up to 1, and all of them are non-negative integers. Right. So now what we will do is we will apply the inequality to some problems. So let's look at the first question where we check concavity and convexity. So we have to look at this question, prove that f of x is equal to sin x is concave on 0 to pi. And we should also check for different functions g of x, which is equal to log x on 0 to infinity. And we can check for h of x, which is equal to tan x on 0 to pi by 2. So we'll apply the theorem that we learned. So the theorem is we check the double derivative of these functions, right? So double derivative f double dash x will be equal to derivative of sin cos x. So that is minus sin x. And this is clearly less than 0, right? On 0 to pi. So therefore, f of x is concave. Similarly, g double dash x would be equal to 1 by x's derivative. So this is minus 1 by x square, again less than 0 on 0 to infinity. So therefore, g of x is also concave. And h of x, h dash x is simply sec square x. So h double dash x will be equal to 2 sec x into sec x tan x, which on 0 to pi by 2 is positive. So h of x basically is convex on 0 to pi by 2. There is another way to prove the same things, but that is slightly longer, where you take, say, 0 is less than equal to x1 comma x2 less than pi by 2, for example, for tan x, right? And you have to show that tan of x1 plus tan of x2 by 2 should be greater than equal to tan of x1 plus x2 by 2. So this proof can also be done. It is slightly longer. So you should try to use the derivatives as far as possible, but you can also do that. So I will leave that to you. Let's go to the second question. Here we have, suppose 3 by 2 is less than equal to x less than equal to 5, we have to prove that root over twice of root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x is less than 2 root over 19. Right. So now this looks like an annoying question with different radicals here. What we will do is we'll look at the function y is equal to root x and think about whether it is convex or concave on this interval, right? So y is equal to root x, dy by dx is simply 1 by 2 root x, and d square y by dx square is basically 1 by 2 x power minus half, so minus half x power minus 3 by 2. So this is minus 1 by 4 x power minus 3 by 2, which will be negative. So this is concave function, right? Okay, so if it is a concave function, we'll apply the concave version of Jensen's inequality later. So first of all, let's think about 2 times root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x. And we can write this as root over x plus 1 plus root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x. We are splitting this term into 2 separate terms, and the reason we are doing it will be obvious now. So we will say that this is the sum of 4 different radicals, right? So we can say that the sum of the radicals by 4, so root over x plus 1 plus root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x by 4 should be less than equal to the root over, basically you have f of x1 plus f of x2 plus f of x3 plus f of x4 by 4 should be less than equal to f of x1 plus x2 plus x3 plus x4 by 4 for a concave function. So I will say x plus 1 plus x plus 1 plus 2x minus 3 plus 15 minus 3x whole divided by 4, right? This is a consequence of concavity of the function and Jensen's inequality applied for y is equal to root x function, with the x1, x2, x3, x4 being these values, x plus 1, x plus 1, 2x minus 3, and 15 minus 3x. So when you add this up, what you will get is 2x and x gets cancelled with the 3x, and you have x plus 2 minus 3, so minus 1 plus 15. So this is 14 plus x. So what you end up getting is root over 14 plus x, and half comes out, is less than equal to this quantity divided by 4. So I will write it on the next screen. What we eventually get is 2 root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x is less than equal to 4 by 2 root over x plus 14, which is equal to 2 times root over x plus 14, right? Now we have this inequality right now. So we know that x plus 1, 2x minus 3, and 15 minus 3x cannot all be equal. Cannot all be equal, because if they are all equal, you will get a contradiction here, right? So therefore, this inequality is a strict inequality. So there is no equal to sign here in Jensen. It becomes a strict inequality if the quantities are not themselves equal. And x varies from 3 by 2 to 5. So the maximum value of this, right, would be less than equal to 2 times root over 19, right? When you put x is equal to 5, the maximum value of this. So the upper limit of the right hand side is 2 root 19. So we have proved basically that twice of root over x plus 1 plus root over 2x minus 3 plus root over 15 minus 3x is less than twice of root 19, right? So that concludes this problem. Now we look at the third one. This one states that assume x, y, z are all positive and x plus y plus z equal to 1. We have to prove that root over yz by x plus yz plus root over zx by y plus zx plus root over xy by z plus xy is less than equal to 3 by 2. Now what we will do here is, we know that x, y, z are all positive. So what we can do is uh, use x plus y plus z, and z plus x as the sides of a triangle, and that helps us convert this algebra problem into a geometry problem, right? So we'll say that triangle ABC has sides x plus y plus z, and z plus x. So therefore, by cosine rule, you can show that cos of A would be, here obviously A is opposite to x plus y. No, actually the triangle sides are like this, A, B, C. So opposite to A side, we can say is y plus z, and opposite to B side is z plus x, and this is x plus y. And then we can say that cos A is x plus y whole square plus z plus x whole square minus x y plus z whole square by 2 times x plus y into z plus x, right? This simplifies as cos A becomes x square plus xy plus xz minus yz divided by x plus y into x plus z, right? We have this as our cos A in this triangle, right? Once we have this as our cos A, we can use the identity cos A is equal to 1 minus 2 sine square A by 2 to try to find sine of A by 2, sine of the half angle, right? I will leave the simplification to you, but you can show that sine of A by 2 here becomes equal to root over yz by x plus yz, which is why we pursued this substitution. Similarly, you can show that sine of b by 2 is equal to root over zx by y plus zx, and sine of c by 2 is equal to root over xy by z plus xy. So we have this stuff here, and we know that y is equal to sine x. You can check the double derivative. Y double derivative is cos x and minus sine x. So this is negative. So this is a concave function, concave on 0 to pi by 2, right? For any x belonging to 0 to pi by 2, it is concave. So our angles are a by 2, b by 2, c by 2. So they are all between 0 to pi by 2. So we can say for a concave function, sine of a by 2 plus sine of b by 2 plus sine of c by 2 by 3 will be less than equal to sine of a by 2 plus b by 2 plus c by 2 by 3, right? Which is equal to sine of pi by 6, which is equal to basically half. So we have sine of a by 2 plus sine of b by 2 plus sine of c by 2 will be less than equal to 3 by 2. And now, since we already know that sine a by 2 and all are equal to root over yz by x plus yz, we have our proof, the required proof, right? Okay, let's look at another one. Here, the function that we have is slightly different. Suppose A, B, C are positive reals, and a power 4 plus b power 4 plus c power 4 is equal to 3. We have to prove that 1 by 4 minus ab plus 1 by 4 minus bc plus 1 by 4 minus ca is less than equal to 1. So here we have to think about what kind of a function we want to guess. Right? So That is the creative part of the solution where you have to think about the function. So you might have to try once and it doesn't work and you try a different function. So what I will say here is we say f of x is equal to 1 by 4 minus root x. Okay. We are getting this. So now here with x lying between 0 to 16 by 9. You will see why 0 to 16 by 9. So that root x lies between 0 to 4 by 3. Okay. Root x lies between 0 to 4 by 3. Now check the derivative here. F dash x is equal to 1 by 2 root x 4 minus root x whole square. And you can find the double derivative also by quotient rule and chain rule. So you will get minus of 3 root x minus 4 multiplied by root x minus 4 divided by 4x root x 4 minus root x whole power 4. And you can prove that for x lying or root x lying in this region, f double dash x is less than 0, right? This implies that f of x is concave. Okay. If f of x is concave here, what I can say is for this function, right? I can write 1 by 4 minus ab plus 1 by 4 minus bc plus 1 by 4 minus ca. Now remember our function was f of x was 1 by 4 minus root x. So that means we have chosen x as a square b square and y as b square c square and z as c square a square, right? That's why I'm getting f of x plus f of y plus f of z as this. Should be divided by 3 should be less than equal to f of this plus this by 3, right? So this will be less than equal to f of that is 1 by 4 minus root over a square b square plus b square c square plus c square a square by 3. This is what is coming because I am saying f of x plus f of y plus f of z by 3 is less than equal to f of x plus y plus z by 3 for a concave function, right? Okay. So we rewrite this like this. We say 1 by 4 minus AB plus 1 by 4 minus BC plus 1 by 4 minus CA is less than equal to 3 by 4 minus root over A square B square plus B square C square plus C square A square by 3. So let's do it on the next page. So we have this right now. Less than equal to 3 by 4 minus root over a square b square plus b square c square plus c square a square by 3. Now, we were given some information about ABC. ABC was all positive and a power 4 plus b power 4 plus c power 4 was equal to 3. This is what we have given earlier. So without loss of generality, we can assume that A is greater than equal to B is greater than C, which implies that A square is greater than B square is greater than C square, right? So now, taking two different sequences, A square, B square, C square, and another copy of it, A square, B square, C square, by rearrangement inequality, I can say that the same order sum is A power 4 plus B power 4 plus C power 4, right? When you multiply the largest ones with the largest one, that will be less than, that will be greater than equal to any other order sum, right? So it will be less than equal to, we have a square b square plus b square plus c square a square is less than equal to this. This is a random order sum taking these two sequences, and this is the same order sum. So from the rearrangement inequality that we did in the last video, we can be sure that this is correct, right? Okay. So here we have a square b square plus b square c square plus c square a square. So we can replace that with a bigger term here which basically makes the denominator smaller and the whole fraction bigger. So we can write, this is correct to write like this, 3 by 4 minus root over, instead of this I'll write a power 4 plus b power 4 plus c power 4 by 3, which is equal to, because in the problem they have said it is equal to 3, this becomes 3 by 3 1. So this is 3 by 4 minus 1, which is equal to 1, right? So what we have shown here is that this quantity is definitely less than equal to 1, which is what we wanted to prove. So actually here, the choice of the function was critical. We chose f of x as 1 by 4 minus root x. We showed that it is concave. We applied Jensen's inequality, and then we used rearrangement inequality to get the fact that we can replace a square, b square, b square, c square, c square, a square with a power 4 plus b power 4 and c power 4, right? So that helped us finally prove this one. Okay, let's look at the next one. This one says find the maximum possible value of constant k such that for all x, y, z belonging to R, x by root over y plus z plus y by root over z plus x plus z by root over x plus y is greater than equal to k times root over x plus y plus z is always true. Okay, so you can see that this inequality is homogeneous. Every term has degree half. Every term has degree half here. And the right hand side also has degree half. Whenever you have a homogeneous inequality, you can always assume things like x plus y plus z is equal to 1. You can assume a statement like this. So we are going to assume that. And then if we say x into 1 minus x whole square is equal to, let's consider this function, this is equal to half into 2x into 1 minus x into 1 minus x. So applying a and gm on these three things, we'll say that that is less than equal to half into 2x plus 1 minus x plus 1 minus x by 3 whole cube, right? This is a and gm on three terms, 2x, 1 minus x and 1 minus x. So this comes out to be 2x cancels and you get 2 by 3 whole cube. So that is 8 by 27 and it becomes 4 by 81. No, 4 by 27, right? So what we know is x into 1 minus x whole square is less than equal to 4 by 27, right? Why is this useful? Because we can write now x by root over y plus z as x by root over 1 minus x. And similarly, y by root over z plus x as y by root over 1 minus y and z by root over x plus y as z by root over 1 minus z. Because we have assumed x plus y plus z is equal to 1 because of the homogeneous nature of the problem, right? Okay, so what we have here is the left hand side can be written like this: x by root over 1 minus x plus y by root over 1 minus y plus z by root over 1 minus z. And we can rewrite it by changing this a little bit. So this can be written as x by 4th root of 1 minus x whole square plus y by 4th root of 1 minus y whole square plus z by 4th root of 1 minus z whole square. And now we bring a x inside this root. So we will say that I want 4th root of x into 1 minus x whole square. So what have I added here? I have added a power of x power 1 by 4 here. So I should multiply the top with also x power 1 by 4. And similarly for all the terms. So I am making this term by brute force here. And similarly here, z into z power 1 by 4 by fourth root of z into 1 minus z whole square. So that is clearly greater than equal to x power 5 by 4. We know that this quantity, we have shown earlier that x into 1 minus x whole square is less than equal to 4 by 27. So fourth root of that will be less than equal to fourth root of this 4 by 27 plus y power 5 by 4 by fourth root of 4 by 27 plus z by power 5 by 4 by fourth root of 4 by 27. And because we are putting a bigger term in the denominator, the whole fraction has become smaller. So the sign of the inequality is greater than equal to this. Okay? So this is becoming equal to fourth root of 27 by 4, and you have x power 5 by 4 plus y power 5 by 4 plus z power 5 by 4. Basically, we have said that the initial LHS is greater than equal to this, right? Okay, now we'll work with this term and we'll say that y is equal to x power 5 by 4. You can take the derivative, y dash is 5 by 4 x power 1 by 4 and y double dash is 5 by 4 into 1 by 4 into x power minus 3 by 4, and this is greater than 0 for positive x, y, z, right? So this is a convex function, convex function. So you can say that x power 5 by 4 plus y power 5 by 4 plus z power 5 by 4 by 3 will be greater than equal to x plus y plus z by 3 whole power 5 by 4, right? So x power 5 by 4 plus y power 5 by 4 plus z power 5 by 4 will be greater than 3 times x plus y plus z by 3 whole power 5 by 4. And the term we had a product of root over 27 by 4 fourth root here, right? So we'll multiply that on both sides. So this is greater than equal to 3 times fourth root of 27 by 4, and x plus y plus z is equal to 1 we had assumed. So this is 1 by 3 power 5 by 4. So if you simplify this, what we get here is root over 6 by 2, right? Or 3 by root 2. So we have proved that x by root over y plus z plus y by root over z plus x plus z by root over x plus y is greater than equal to root 6 by 2 into root over x plus y plus z, because we have assumed that this is 1. So our value of the constant k is root 6 by 2. If your constant k is greater than equal to that, then you are always assured that this is the maximum possible value of the constant basically for which this works. Let's look at one final problem. In this one, we approach a trigonometric problem. Let n belong to natural numbers and n is greater than or equal to 2. Prove that when x belongs to 0 to pi by 2 power n, you have cot of 2 power n x plus n by sine of 2 power n plus 1 minus 2 by n into x is less than cot x. This is what we have to use. You have to prove, right? We will look at this identity. The identity is cot 2x plus 1 by sine 2x is equal to cot x. And we'll use this identity repeatedly. First, we should try and prove this identity. It is pretty straightforward. So what do you say is 1 by sine 2x is equal to cot x minus cot 2x. Therefore, 1 by sine 4x would be equal to cot 2x minus cot 4x. And if you keep adding like this, it will become a telescoping series. So final term I will take is 1 by sine 2 power nx will be equal to cot of 2 power n minus 1x minus cot of 2 power nx. And if you add all the terms, what you end up getting is 1 by sine 2x plus 1 by sine 4x, so on, till 1 by sine 2 power nx should be equal to, this becomes a telescoping series, all the terms get cancelled except the first part and the last part of the first and last term. So this becomes cot x minus cot of 2 power nx, right? Now this series is what we have right now, and let's write that conclusion that we have written, 1 by sine 2x plus 1 by sine 4x till 1 by sine of 2 power nx is equal to cot x minus cot of 2 power nx. Now let's consider the function f of x is equal to 1 by sine x. You can show that f double dash x is greater than 0. So this function is convex on 0 to pi by 2 power n. So since this function is convex, therefore f of 2x plus f of 4x plus so on till f of 2 power nx is greater than equal to n times f of 2x plus 4x plus 2 power nx by n, right? Now the sum inside is becoming f of 2 power n plus 1 minus 2 times x by n, right? Correct. So this is n times this. So we have this left hand side here, f of 2x is 1 by sine 2x, f of 4x is 1 by sine 4x, and so on. So therefore that should be equal to this, right? So left hand side is cot x minus cot of 2 power nx is greater than equal to n, and this is f of this. So this is 1 by sine of 2 power n plus 1 minus 2 by n times x, right? So what we have now is if you bring this term on this side and bring this term on this side, you will actually you just leave the cot on one side and bring the cot part 2nx on the other side. So we will be able to show easily that cot power 2 power nx plus n by sine 2 power n plus 1 minus 2 by nx is less than equal to cot x. This is what we wanted to prove. So here in this question, what we are using is Jensen's inequality on f of x is equal to 1 by sine x, after showing that it was coming as a convex function, and the identity cot x, cot 2x plus cosec 2x or 1 by sine 2x is equal to cot x. And this identity, when applied multiple times, becomes a telescoping series, which helps us simplify the whole problem. So that's about it for Jensen's inequality and convex functions, and we'll continue with a new section in the course in the next video, and that's a good point to stop.